um, afternoon, or can you guys comment on the live stream? Just want to double check. Anyone? Okay, so I take it that either the chat is disabled or you guys do not have an account to comment on. Anyhow, we might as well just start. So what I'm gonna do is today will be just a very short session, but this will ideally just go through the very basics that you guys need before starting like year 12 physics. This isn't an actual topic, by the way. It's just one of those side topics that they add to different year 12 and 13 questions, and everyone tends to get them wrong because no one, I guess, went through them beforehand. So what we'll do is, this is the first question I'm going to pose to you guys. What will be the smallest reading possible on the following devices? So I did steal this from school, no one needs to know that. But if I show you this very quickly, what do you guys reckon is the smallest possible reading on this? That's my question to you. So this will answer the what's it? Smallest reading for this. Now I'm hoping, since no one can comment, but I'm hoping you guys are gonna say it'll be what 0.0 and then the smallest number there could be 1, right? So the smallest reading that you can get on this would be 0.01, and then it'll be amps, right? Now, imagine this was a voltmeter. I didn't take a voltmeter, so, but a voltmeter is pretty much identical to this, so it'll also be 0.01. Now comes the slightly easier part. For an actual ruler, what would the smallest increment here be, or the smallest reading? So we know it goes up in centimeters, but you can also go down further. So as you guys can probably see, start off with 0 centimeters there, then it'll be 1 millimeter all the way to 10, right? So what we can basically say is that is 0 centimeters there. This is 1, and we know that each one of those smaller lines represents 1 millimeter. So for a ruler, it'll be the smallest thing we can measure is 1 millimeter there. For a mass balance is very similar to the diameter. I just drew a rough sketch there, but they usually tend to measure to this as well. Yeah. A thermometer. Pretty sure anyone who uses a thermometer knows that the smallest reading is basically, they tends to go up in 1 degree Celsius, like up in 1 degrees. So we'll just say 1 degrees there. Yeah, so these are all the smallest readings that you can get on these devices, for the most part, obviously. And what you need to know in A-level physics is that these smallest readings are known as the resolution. So the key thing here is whether the smallest reading will be called this. And you also now need to look at what the benefits of a high resolution is, right? When we deal with science, this will help you in biology and chemistry as well, math as well. But if you have something that has a very, very high resolution, that means that you have a better accuracy, right? So what we need to know is in physics is that you will get a better, probably can't spell that, but you get better accuracy there. So an example is if you look here once again, so this ammeter is what, 0. Let's imagine the value on this ammeter was 0.02 amps. Let's say I have another ammeter, so this is one of my ammeters there. Let's say I have another ammeter, but this one can only measure up to 1 decimal place. So because my real value is 0.02, so this is the real value. But because this ammeter can only measure up to 1 decimal place, it will just read 0.0, right? Because if you round this to 1 decimal place, this is less than 5, so it'll just still be 0.0. So that's not really good. Yeah, so basically, the more decimal places you have, the higher the resolution, and therefore the better the accuracy. So you probably may know this from your GCSEs, but tends to be a high level stuff. Okay, Now the next thing, this is where we get into complete just A-level stuff. If I was to measure, let's go to a different page. Let's say I was to measure this thing, right? I was to measure the length there. Now, I'm hoping you guys would notice there's two different issues here. So one of the issues is that I cannot say for certain that I've aligned it correctly. So I cannot say for certain that I aligned the 0 centimeters to the edge there. It's all down to your perspective and how you're looking at it, right? So there's one issue there. Additionally, there's another issue at the very end there as well. So there's 2 points, the start and the end, where I have some uncertainty. So what we can basically say is with a ruler, this is the number one thing they always ask you in the exam, the number one instrument. So ruler, with a ruler, there is 2 points of uncertainty, right? So by logic, there'll obviously be one of them because we can't say this is exactly 0, and we can't say that's exactly 6 there. So there's 2 points. Now, uncertainty in physics, the way it works is with a ruler. So actually, I might as well just measure it now for you guys. Let's pretend this is eye level. This will be about 5 points, I don't know, 5.8. Yeah, so let's just say length is 5.8. Anyone in the world can do this. But now to find the actual uncertainty, what I'm going to say is there's uncertainty at the beginning and there's uncertainty at the end where we measure that. So we say at the end. And the value for the uncertainty depends on the resolution. So if you go back to the first page, the resolution of the ruler, or the smallest measurement you can get on a ruler, is what, 1 millimeter, right? So that's going to be that is pretty much going to be what this is. So the way it works is we look at the smallest increment, which is 1 millimeter, and the uncertainty is basically half of whatever the resolution was. So AKA we'll have half a millimeter there of doubt, and then you also have half a millimeter at the back there as well. Yeah. So the thought process, what I've done was, just in case it's a bit confused, and probably is, my thought process was find the smallest resolution on the ruler, which is 1 millimeter, because that's the smallest thing, divided by 2, because in physics you're always half the resolution. Chemistry, they leave it as it is because they're rubbish, but yeah. So divide resolution by 2, giving us 0.5 millimeters. And this is your uncertainty. All we said now was we got two different points of uncertainty because you have to have a starting point and an end point. So therefore, you're going to have uncertainty at the beginning, uncertainty at the end. Now, your overall uncertainty basically for a ruler will then just be 1 millimeter overall because you have 2 points. Yeah, so what we can say is our final answer will be 5.8 centimeters plus or minus, give or take, 1 millimeter of uncertainty. Yeah, what I'll do is let's just do another one very quickly. This, by the way, is all like A grade year 13 stuff. It's not even basic stuff, by the way. So if you get this, like, you're a legend. Let's use a different. Let's say you want to measure the length of the black ink. Yes, because obviously it's not long enough. So let's just measure the length of the black ink there. So it would be roughly 4 point, I don't know if you guys can see it, too much glare, but 4.7. Yeah, so what we can say is length of ink is 4.7 centimeters. Once again, because we're using a ruler, we have doubt where our 0 point is, and at the very end where we measure as well. So 2 points of uncertainty. And how much is the uncertainty? Remember, in physics is always half the resolution. So resolution, or the smallest possible value here, is 1 millimeter. Right? So we just need to half it. So you get 0.5. So because there's 2 points, there'll be 0.5 at the beginning, 0.5 at the end. So your total uncertainty is basically 1. So it'll just be plus or minus 1 millimeter. If you want to memorize it, you can, to be fair. If you just know that a ruler always has this much uncertainty, it's much easier, but yeah. All right, so that's for that. Now you see with a ruler, you have doubt on both sides. If I gave you guys a thermometer, let's say that here it read roughly about 38 degrees. Is there any doubt that it began at 0? This is the question to you guys. May or may not be like a ruler. So is there any doubt, or do we really need to look at where the 0 point is with a thermometer? Or do we just only take the reading of wherever the red mercury reaches? I'm hoping you guys are thinking of the latter. So a thermometer, you only take a reading of the top value, right? So you only take a reading of the top value. You never look at the bottom and then look at the top, right? So only take a reading of the value given. So it might be like 38. So how many points of uncertainty do we have? We know that the bottom is guaranteed to be 0. It's calibrated in a lab. So there's only 1 bit of uncertainty at the very top there. So unlike a ruler, which has 2 points of uncertainty, a thermometer only has 1 point. Yeah, so we only get 1 point there. So if I was to show you how this would work now, it would basically look something like this. So I'll do both alongside each other. It's bad that you guys can't comment, because otherwise I have no way of knowing whether you guys understand this. So let's say this thermometer is basically 36 is there, 37 degrees is there, and let's say the mercury basically reaches about there, right? So what we know is that it's somewhere between 36 and 37, and this is the methodology that I'll always do. So I write down what the resolution of the device is. For a ruler, it was 1 millimeter. For a thermometer, it goes up in ones. So just 1 degree Celsius. That's the smallest possible value you can get. And then next, what we want to do is, we know it's between 36 and 37. In physics, if it's between two numbers, if you can see it closer to one number, you just pick that number. So it's closer to 37. So all we'll just say is, so our temperature is 37 degrees. And now we need to find out by how much are we out, potentially. So what we do, the golden rule in physics is, we know the resolution. Physics, uncertainty is always half the resolution. Yeah, so you have to half your resolution. So it's 1 degree Celsius divided by 2. So the uncertainty is basically half a degree Celsius. So it's plus or minus by a half. Yeah, so, and because there's only 1 point that we're uncertain at the top there, because the bottom is calibrated, so it will just be 0.5 degrees Celsius. That's how you would answer this like 3-marker in the exam. Yeah, so you always find the resolution first, which is just the smallest value. And it's always given in the exam question anyway. Now, let's just do another ruler one in contrast, just to show you that I'm doing the same. Let's say that we measured something, and this length gave us 4.1 centimeters, right? So let's do the same steps like we done for the thermometer. We'll write down the resolution of the ruler, which is the smallest possible value you can measure, which is 1 millimeter. For anyone who joined late, you can tell because centimeters there, millimeter is one of those tiny dashes, right? So the smallest possible value is 1 millimeter, like we've done there. Next off, we find the uncertainty, which in physics is always half the smallest number. So you're just going to do 1 millimeter divided by 2, like we've done there. Gives you half a millimeter. The only difference between a thermometer and this is that with a thermometer, you're guaranteed that you start from 0. Whereas here, you have to kind of align it yourself. So there's human error or 0 error there. So there's 2 points which we're unsure, the start and the end. So that means you just have to use like this in 2 positions, or just double this, if that makes sense. So let's say this was 4 centimeters. It'll just be plus or minus 1 millimeter, because you had half a millimeter of doubt there and half a millimeter out here as well, is to get 1 millimeter. So that's how you do it for these two. I have no idea whether you understand this remotely, but yeah. Basically, the year 13 still do not get this, so take it how it is. It's probably the hardest topic because it's very abstract, but that's what you get for that. Obviously, in class, a lot easier to teach this because you can actually use the equipment. Now, let me show you the slightly easier stuff. So, there's two. Now, you see with uncertainty, we basically said, so let's look at this, for example. It tells you the measurement, and then it also tells you by how much you are out by. This is the same unit as that, obviously. This is known as your absolute uncertainty. So, absolute uncertainty is where you're given the uncertainty as a measure of your normal unit. So, if you're working in resistance, then your absolute uncertainty will also be in ohms as well, right? So, that's that. So, in this question, let's do this together. It says, what is the absolute uncertainty? It's just this. Yeah, and it has to be the same units as that. So, we're just going to say plus or minus 0.1 ohms. And then the next thing is percentage uncertainty. Now, you guys are probably all good at math. To find percentage, we want to know how much is this out of that, if that makes sense, yeah? So we're just going to do this, which is your absolute, out of your total measurement. And if you want in percentage, pretty sure you guys know what to times this by, right? So, believe it or not, you'll get like 2 marks or 3 marks for this in the exam. So 0.21 divided by 25 times by 100. And I think you guys get 0.4. You can have decimal percents in A-level physics. It's just a bit weird, but you can. So you get that. All right, I want you guys to... So that's how you basically convert this. It's just weird that no one can comment. But let's try basically... Attempt these ones yourselves in your calculator. See if you can do it before me. So we want to go from absolute to percentage, just like we done there for these ones. Yeah. So absolute is this much, and we want to go into percentage. So it's just this over your total measurement times 100. You guys probably will finish this before me, but meh. Okay, I got 0.18 recurring percent. I'm breaking all the laws of maths here. And then let's do this next one. So 1 over 680 times this. Now, the key thing, guys, I should have done it myself here. Just always double check that these units match, because sometimes they can make this centimeters and that millimeters. So you'd have to convert this into whatever units the reading is itself. So 1 over 680 times 100 gives you 0.15, I'll just say. Bam, done. Oh, there's another one as well. Okay, I'll do this one a bit quicker. So this, I'm pretty sure you guys are all like just breezing through this very easily. If you guys survived till now, good job. So this one is what, 0.003, I think, recurring percent. Now, the key thing is, in physics or in science in general, you basically want this number to be as small as possible, because the less uncertainty you have, the better quality your results are. So this looks really good. Okay, now, obviously, we've done absolute to percentage. Now, you probably guessed it, they also want percentage to absolute. So they want you to basically what they're asking you here is, what is 2% of 60? Now, come on, guys, it's like a grade 4 or 5 math question. So like, what is 2% of 60? Now, off in math means multiplied. So all we need to do here is, we can just write this as a fraction. So 2 over 100, which is 2%, times by 60. Yeah, because off means times. So that would be, now I can't do mental math. Things 1.2. And you write the units, because now we have absolute. Absolute is to do with actual physical quantity. So the final answer would be 60 plus or minus 1.2. You write it neatly like that. Yeah, let's try the next one. So they want 0.01% off that much. So percent just means divided by 100. And then off that much just means times by whatever that is. So what do we get? We get, oh yeah, because that is pretty small. 0.003, is it? I think. Yeah, so we get this for it. So our final answer is 32 plus or minus 0.003, and the units is centimeters. Yeah, so I'm hoping this is not too bad, at least this specific section here. Just know that absolute has units based on the actual reading, whatever you're trying to measure, and percentage, as the name suggests, just to do with percentage. Yeah, so that's how you do these two. Um, Now, the thing about the very, very beginning about rulers and thermometers, do not worry if you forget or don't understand this bit. We'll go through it again in class whenever we start it again. But this, I think this is a bit more important. This is what we use it in literally almost every physics question. Actually, I lied, not almost every, but like there's a paper in A-level physics that focuses solely just on practical. So you get all this kind of stuff in it. So this is probably the most important part of the lesson, and thankfully is a lot easier than what we've done before. So if you know this is really good. Okay, now the last thing before we end the live stream is what do we do when we deal with multiple readings, right? So let's say this is a let's say Mr. Hemin left his house, went to a shop here, and that distance was 2 meters. I have no idea how is that close to his house, but anyway, 2 meters there to the shop. And then let's say from the shop he went to school, and that is an extra 5 meters, right? Now he's using some garbage Apple Watch that tells you how far you traveled distance-wise. So he gives him this reading first for that journey. Then he gives him this reading for the journey from the shop to the school. So what we want to know is what's the total journey and what's the total uncertainty. So what we can do is when it comes to the same units or the same like measurement distance, for example, you can just add that the actual measurement. So 2 plus 5, ignore the uncertainty for now, is 7. So we traveled 7 meters, and then now we're going to find out how much uncertainty there is. Because they're the same units, yeah, because they're both in meters, you can literally just add them together. It's like a cheat code. So 0.1 plus 0.2 gives you 0.3. The key thing, guys, is you can only add the absolute uncertainty, like these uncertainties, when you have the same units. So when we deal with distance, if you add distance and speed, then you cannot do that. Yeah, so it has to only be with the same things. All right, try it for this one. I want you guys to find the. Let's just imagine these are 2 times you ran. And what's the total time? So the total time will just be normal numbers. 6 plus 5 equals 11 seconds is the total journey time. And this S just stands for seconds, by the way. It looks like it's a 5. So what is the total uncertainty? They have the same units, so you can just add them. 0.1 and 0.1 make 0.2. There you go. All right, now to make it a bit more challenging, let's find the percentage uncertainty for both journeys. So percentage, we've done this before, is going to be what? Your absolute over the total times 100. Because we're trying to find out how much is this out of that as a percentage. It's just good practice to know how to go between one and the other. You'll be surprised how many marks you can rack up in one exam. So if you times about 100, you get 4.28. Now, if you guys are probably not aware of this, but in A-level physics, you can lose up to 20 marks in an exam just if you do the wrong decimal places consistently. So it's very strict. So if you look here, the smallest resolution we have is basically to one decimal place. So you'd want to match it. So here we get 4.28. So we'll just make it 4.3. Yeah, so 4.3%. So basically, this was in absolute terms, right? Because it actually has the unit there. Now, to write it in percentage terms, it'll be 7 meters plus or minus 4.3%. They're both uncertainty. It's just that one is in absolute, one is in percentage. Okay, so that's how you do it. Now, the last 1 minute we're done, is let's say a question basically had both speed and time, or like distance and time, two different measurements. So let's say journey time is say 10 seconds plus or minus 0.1 seconds. And then let's say distance 400 meters plus or minus 0.1 meters. Okay, now when it comes to this, I always tell my students like ignore the uncertainties for now, find out that what the normal value is, and we do and say they want you to find what speed is, right? So this is the question. So this is like an A grade question in year 13. So we need to find out the speed. Now we know from GCSEs that speed is equal to what? Distance over time. Oh, the good thing is you guys will get a formula booklet next year anyway. So every single equation you need is given. So distance, which is 400, divided by time. Don't worry about the uncertainties. We'll deal with them afterwards. Gives you 40 meters per second. Yeah, so that's our speed, just a normal value. Now we need to find the uncertainty. With uncertainty, you guys can see that you have different absolute uncertainty units, meters there and seconds there. Now, absolute uncertainty will not work because the units don't match. So what uncertainty could we use that have the same units? So we know that absolute will not work here because the units are different. So the only thing left for us is to make both of these into a percentage uncertainty for each, and then you can add them. Yep, so the way it works is, let's find out the percentage uncertainty for each. So let's do it for journey time first. So the percentage would be absolute over the 0.1 over 10 times 100, which I believe will give you 1%. So that's the uncertainty for the journey time. All I done was 0.1 out of 10, percentage-wise, what will that be? Now let's find the percentage uncertainty for the distance. Same thing. Absolute uncertainty for distance is 0.1 meters. And you need it as a fraction of the total distance times by 100. I have no idea what this gives. Gives you 0.025. Okay, so 0.025%. So this is by how much you are off by potentially for your time, and this is how much you're off by potentially for your distance percentage-wise. Notice how the units are the same because it's percentage. So now you can just add their percentage uncertainties. You're probably wondering, I bet someone has this question. Because you divide the distance and time, should you not divide the uncertainties? The answer is no, because if you think about it, basically you have some error in your time, you have some error in your distance as well. So you have to add them up because overall it'll give you more error for your speed. Yeah, so you're combining stuff. Whether you divide them or multiply them doesn't matter. You still have to just add up the percentage uncertainty. So 1 plus 0.025 will give you your answer. So 1 plus this gives you this. And the final answer, guys, what's your actual speed is 40 plus or minus. What's the uncertainty? Percent. There you go. And if you wanted, you could have obviously then changed it back to absolute by doing this over 100 times that if you wanted. But that's how you would do this. In all, I know that I keep blowing things out of proportion, but honestly, guys, if you get this, then that's pretty good. Like this is easily like an A grade question in year 13 as well. So it's quite, yeah, if you get it, well done. So that's just a glimpse of like the basics, I guess, of A-level physics. The thing is, A-level physics is very interesting. This is just basically, how do I explain it? The boring bits that you need to do before starting the course, which is like really annoying. So don't worry, there's nothing to do with the content. It's just an additional thing that shows you how we get better quality results in science in general. So yeah, I hope this was I guess, informative somewhat. All right, take care.